All right, let's talk about doing spot welds inside Ansys LS-Dyna. Um, I'm going to present three different ways to do this, right? They are very similar to each other. Basically, the idea for spot welds is that we're essentially creating a constrained nodal pair between the two body. Usually, imagine two different sheet metal parts that we're sort of spot welding together. But in this case, there are three different methods with some differences between them. Some are easier to use, some are harder to use, but some are a little bit more powerful than the other. I'm going to quickly show how to do each, and then what the differences are and what the limitations are. Okay. Basically, the method number one is to do something called a constrained spot welds. So constrained spotwelds is essentially this thing inside the documentation. Always go to documentation for everything, right? So basically, we're essentially generating a mass of spotwelds, right? So it's essentially like not exactly a weld element, but basically it's like a little connection between two different nodes that we're going to be linking together. Uh, uh, in general, right, the basics principle behind it is that, as you can see here, the blue part is like a sheet metal, the red part is another sheet metal, and those two nodes are being linked together by this constrained spot welds. Basically, this thing allows us to define a failure criteria in normal and in shear, right? So for example, I can pull these two sheet metal apart. Once it exceeds the shear force or the threshold, it's going to pull it apart, basically allow that to fail. What I can also do is to define a EP parameter, which is the effective plastic strain. So that's very similar to modeling, say for example, as imagine try to pull apart a two piece of sheet metal that's been welded together, right? Usually you don't see the weld itself fail. Sometimes the material around the weld will fail first, and that's where you can model essentially with the EP parameter. Basically, you will look at the plastic strain around that node, and if the nodal plastic strain exceeds that value, you'll break apart at the nodal connections. So that's another way in which you can model the failure of a spot weld. Now, in terms of limitations, right? Because the way this functionality works, you can really only connect nodes with rotational inertia, right? So we can't really do this for solid elements. Solid elements has only translational DOF, right? It doesn't really have the rotational degree of freedom that we needed. So for solid elements, you have to use the constraint rivet, which I'm not covering here, but you can imagine it to be very similar. The nodal pair itself must not be coincident, and then we must make sure that there are no other constraint on these nodes, which is pretty much like you expect it to happen. You can't really have a nodal constraint when you have multiple nodal constraining the same node. That's usually is not allowed, right? Okay, so with this, I'm going to do a quick demonstrations, right? So as you can see here, what I have here are two different sheet metal pieces, right? Um, these two pieces, I'm just going to assign sort of say something like a 12.7 millimeter, which I think is like 0. Or actually these should be 0.1 inches. So let me go ahead and change these to inches to make sure my units are correct. And then let's change it back to millimeter for the rest of the model, right? And then I'm going to mesh these two parts. The default size is okay. What I'm going to do here is that because I'm going to make sure the mesh itself is structured, so I'm going to apply two-phase meshing on these two things, and then go ahead and mesh it. Now, what I want to do in this case, right, I'm going to tie this node and this node together, right? That's what I'm going to do. Now, so to use the constrained spot weld card, what I'm going to need is the node ID of this node, which is 33, and I'm going to need a node ID of this node, which is 106. Okay, as I've always done these type of things, right, what I have is a bunch of pre-prepared card that I usually use for my model, right? So in this case, I already have the constrained spot weld model card ready to go, and then I'm going to go ahead and copy this. And then I'm going to write out a command object, which is the Dyna keyword. In this, I'm going to copy this in here. Now remember, my first node is going to be 33. My second node is going to be 106. Right? Let's just double check that again. Right? First node is 33. Second node is going to be 106. Okay. Now, and then the SN and SF are the normal force requirement threshold for failure, and then shear force requirement for failure. So as you can see from the documentation, right, the SN is normal force failure criteria, and the SS is the shear force failure criteria. So in this case, what I'm going to do here is I'm going to do 10,000, 10 kilonewtons and 50 kilonewtons for failure criteria. The other four parameter I'm going to leave as default. These are essentially exponents for some additional mathematics, and these are the sort of the failure time and such, which we don't need to worry about. We're also not defining any kind of plastic strain requirement in this case, so I set it to be extremely high. And that's all we need to worry about for now, right? So basically, we're only allowing the spot weld to fail after there's an enough force between the two pieces of sheet metals to pull it apart. Or we're not allowing the sheet metal itself to fail by using the EP parameter in this case. Okay, now the rest of the model is very simple. I'm gonna go through it pretty quickly. I'm gonna set a 2 millisecond termination time, right? And then I'm going to set a fixed support on one end, and I'm going to set a displacement on the other end. Very simple, right? So one is an SBC support, one is a prescribed motion that we're going to be applying. And in this case, I'm going to do a 2 millimeter prescribed motion. Actually, I'm sorry, a negative 2 millimeter prescribed motion on in the other directions, right? So that's going to pull this thing apart to try to challenge the spot weld into which we put together through this card, right? So I'm going to change the name here to call it Constrained Spotweld. And then the last thing I'm going to do is I'm going to go ahead and write out a database card. Usually it's a good habit to have a couple of your own database card, but for the purpose of what I'm doing here, right? Or what I usually like to do is to make sure I can get enough sort of data from the solution, right? So in this case, I'm gonna write a D3 plot at 100th division of the termination time, right? So give me 100 data points to look at. And that's it. Let's double check the model. I have two different sheet metal parts, right? I have two different sheet metal parts. They're being assigned as steel material. I have created a spot weld between these two sheet metal parts by linking the two nodes together, right? Remember the two nodes that we're linking is this one and the one below it. I have a fixed support on one end. I have a displacement on the other end, right? So my expectation is that I'm going to challenge the spot weld until I pull it apart. And the requirement for on the shear direction is 50,000 newtons. And that's what I expect the failure to be. Okay, good. Let's go ahead and save. And let's go ahead and write out the input file. I'm going to write it out into the demo constraint spotweld directions. You know, a good habit to get into always, right, is to check your input file to make sure it's correct. So let's go ahead and do that. I'm going to go ahead and put the input file into our spread post and just take a look at it. Now, one thing that's worth taking a look, sort of pay attention to is that you can sort of see, right? You see there's this little beam, almost look like a beam that's created between those two nodes, right? And that's what's actually happening in the input file. So when you open up Atlas spread post, it actually allows you to see that this has been correctly generated. What we can also do is do a general model checking to make sure there's no major error in the model and there everything looks good. Okay, I'm gonna go ahead and close this and go ahead and run the model. Come on, there we go. All right, let's go ahead and run the model. Because model is so small, I expect to finish almost right away. All right, there we go, it's done. Okay, let's open up Atlas spread posts. And then I'm going to pull the results in here. 1 second. All right, so I can sort of see. Eventually, this thing will come apart. Yeah, after a certain while, it will come apart. Alright, so what I'm going to write, while this thing is running, I'm going to write out the input file, write out the binary data. Let's take a look at it. So the SBC force for one side in the Z direction, as you can see, this thing is this is very noisy data, so I'm going to filter that a little bit. do a moving average. You can sort of see this thing fills at exactly 25,000 newtons, right? And I'm gonna look at on the action side, which is the BND out. I'm gonna look at the BND out. I'm gonna select all the nodes, and I'm gonna sum it together using Z total. You can see this is at 25,000 newton, right? Around time it failed. Let's do the same kind of filter. Right, so reaction side 25,000, action side 25,000. That tells me exactly that the Spotweld failed at exactly 25,000 newtons. I'm sorry, 25,000 newtons. So let's take a look at it together. Right, so the weld is going to be put apart until it reaches this point, and then the pieces will basically fall apart. As you can see, start separating. You can sort of see the separations there. Right, and that tells me the Spotweld is correctly generated. All right, thank you very much.